And then I'm going to introduce you, Mohammed, and then we'll get started here. Okay, so in the tiny box there, maybe you want to shut your presentation down so people can see you while I'm introducing you. Because you're just a tiny little box right now. There you are. And it's lovely to see you again. So Mohammed M. Jalalzai was a postdoctoral researcher in the blockchain at UBC cluster. He received his master's degree in computer science from Technical University of Berlin in 2010 and his PhD from Louisiana State University in 2019. His research is mainly focused on distributed systems, more specifically on designing, implementing, and testing secure, efficient, and scalable Byzantine fault-tolerant consensus algorithms for blockchain networks. He's also interested in the intersection of machine learning and cybersecurity. And I would say that Mohammed is, I feel like, somewhat famous as being
I hope so.
the inventor, or at least one of the inventors of the BFT protocol Fast Hot Stuff. And Fast Hot Stuff is still, I think, the world's fastest permission blockchain protocol, and is being used in a number of blockchain projects. So really great work, Mohammed. You are a star. And so Mohammed, he of course, is focused on efficient and secure algorithms. And so he's going to talk to us today about how he's taking his work now into the work that he's doing with Monad, which is exciting. We're really excited to hear about. So over to you, Mohammed. You should be able to present your slides again now, and we're looking forward to your talk. Thank you so much.
Thank you, Dr. Vicky. Thank you for the great introduction.
Oops, hang on a second.
Yeah.
Make sure we're getting volume.
So, yeah, hello, everyone. Yeah, I'm Mohammed. Yeah, people also call me Mussadiq here as well. And I'm a senior researcher at Monad. Today, our talk is about scaling decentralization and all the improvements that have been done in Monad. So it includes some of my work, but also the work of my colleagues. This presentation, most of these slides are prepared by Kevin Galler, who is our developer relation. And I did some minor adjustment for the talk, so just to give him some credit. Let's go over the goal and the challenges that we are facing. We know that EVM is the widely used environment for writing smart contract codes, but EVM does not scale. Its performance is terribly slow. Though Ethereum that uses EVM is highly decentralized, but we still have the problem with the scalability. So if we look at the performance of the Ethereum, the throughput is on average is 10 transactions per second, or it can be translated into 1 million transactions per day. And assuming you have an app with 1 million daily active users and each user perform 100 transactions per day, then you will need at least, then this app will need to have at least 100 million transactions per day, which basically gets translated into 1,000 transactions per second. And well, that cannot be supported by the EVM. So one of the problems is the gas is conservatively assigned. It's because the consensus is too slow. There are issues with the storage. EVM itself is single-threaded, so this means operations are executed serially. And then the consensus and executions are also intertwined, so they are interdependent. You cannot move, and you cannot move the consensus to the next stage until execution is done, and vice versa. And state also grows. The size of the state grows significantly over the time. And then we have like some L2s currently being run over the Ethereum L1, but there are many issues with these L2s as well. So most of the high performance L2s are basically centralized. Though they mention that they leverage the Ethereum's decentralization, but the fact is that you can't leverage Ethereum's decentralization until the transaction that L2 puts on the Ethereum gets finalized. So basically, the actual latency of L2 is similar to the latency of Ethereum, unless if you want to trust the L2, this centralized sequencer, then that's fine. But then it's very similar to using a Web2 service because you are trusting a centralized entity. The other problem with L2s are like block space and the liquidity is fragmented because there are many L2s, and then they have to compete for data availability and the block space. And many of them are not that mature as well, and there are compatibility issues with the EVM as well, because L2s may not need all the functionality of the EVM, and then they probably might have narrowed down their functionality to make it more lighter to run, but then it causes compatibility issues. So why Monad is not L2, but it's L1. So by being L1, Monad is able to achieve 1,000 times more throughput. In reality, it's even more than that, but probably it will be revealed sometime later. The other advantage is that the block space is larger. So this allows more transactions to be included, and it reduces the gas costs. And then the finality is way faster. Ethereum's finality is generally between 1 to 2 slots in each slot. Epoch, and each epoch has 32 slots, and each slot is 12 seconds. So that's in the range of 20 to 30 minutes, whereas here you can get finality in 2 seconds. And then it avoids all these cons or issues that comes with the L2s. But this is so that was about the actual consensus. But now, if we look at the EVM or virtual machine, that is also not scalable. It can execute up to, on average, slightly higher than 300 transactions per second, which is another problem. So even if you improve the consensus, you get stuck with at the EVM or the smart contract level. So what is actually Monad? So it's EVM equivalent L1. So it's not EVM compatible, but it's EVM equivalent. And then it has very high performance of 10,000 transactions. It's at least, and the blocks also allow more number of transactions, and hence it also allows larger number of supports higher threshold of the gas to be used for the execution of transactions. Block times, which is basically the propagation time of the block, and then basically one round of consensus is 1 second. So in 2 rounds, you get the block finalized. Actually, we are even improving this, but that paper and those results will appear maybe in a few weeks. And then it's decentralized. Currently, the goal is that to support hundreds of validators, and now, but it will also be scaled to thousands of validators. But of course, when you're launching, you don't want to scale very fast. You want to scale to make it decentralized and add more validators slowly. Yeah, so basically you can put any contract application that runs on EVM, you can just put it to Monad, and you get all the advantages of the Ethereum plus the performance of Monad. So it's compatible to the Ethereum RPCs, and it runs basically the same EVM that Ethereum runs. And then the gas cost is significantly cheap. So this allows developers to add specific assertions or conditions in their code and without worrying about the gas costs. So basically, if we see Monad, we know Solana is a very high performance chain, and then but Ethereum is EVM compatible. So basically, Monad's protocol has way more stronger guarantees and higher performance than the Solanas. So it's basically a combination of higher performance and EVM compatibility, and also achieves decentralization. So it's a scaling and decentralization along with the EVM compatibility. So you can put an EVM smart contract over the top of it. So what are the basic problems in the blockchain that has been addressed in Monad? So the main constraints that we have is network bandwidth. It's always expensive. CPU throughput, accessing the states and the hard drive, and then the state growth. So there are possible shortcuts, like you can increase the bandwidth or put the validators in the same region, but putting validators in the same region creates security issues. So someone just it's not you want your validators to be decentralized and scattered throughout the world. At the same time, adding more bandwidth will increase the cost of a validator. So whoever operator that runs those validators, it will have to incur additional costs, and we don't want that. It's same with the SSDs. You can increase RAM and then add the data into the memory, load the data into memory, but then it costs a lot. So basically, the goal of Monad is that to use a commodity device, so commodity hardware, but provide higher performance and scalability, and make sure that the nodes can be geographically decentralized, which improves the resilience of the network, and also provides equal opportunity to the different node operators and the different parts of the world to take part in the network, instead of centralizing the network to a specific region. So Monad architecture involves improving of the improvement of different layers, the consensus layer, the execution layer, and as well as the database layer. So Monad BFT is basically so in Monad, one of the improvement that has been done is that it has separated the consensus and the execution. So consensus only orders the transaction. It does not wait for the execution, whereas in the normal or traditional consensus protocols that we see, if there is an order transaction, the validators have to execute it, and then there has to be another round of consensus. So consensus is always blocked by execution. So in Monad, consensus is not blocked. It only orders, and then execution module does the execution. So there is separation of execution and the consensus. And then consensus has a linear communication. They have, we have tried to improve the message complexity so that larger number of validators can be added into the network, and the number of messages exchanged should be kept to minimum. And the protocol currently that we are using is very similar to the two-phase hot stuff, fast hot stuff, or DIM. So it's very similar to these consensus protocols. There are improvements done at the signature aggregation level, and then there is improvement done at the network layer where messages are propagated using erasure coding. We'll discuss it, how that improves the performance. And the consensus, as I said, is very similar to fast or DAM. And if a block is proposed by the first leader, Elias, then after 2 blocks are added over the top of it by Bob and Charlie, that block will be committed or finalized. So we have basically 2 rounds of communication. And since it's a one-to-many communication, the block is proposed and everyone sends a vote to the next leader. So the message complexity is also linear. So this allows the protocol to be able to add more validators. As I say, we have done improvements, additional improvements to this design, which make the protocol even more efficient and robust. But that will be that work will probably made public in a few weeks. So data or block propagation is also one of the bottlenecks, and any consensus protocol. Since block size is large and the leader has to send it to everyone, and that causes bottleneck at the leader. And what we do is you don't have, a leader doesn't have to send the entire block. It basically builds the encoded chunks of the block and send those small chunks to everyone. And then everyone shares the chunk that it has, and then eventually everyone is able to build the block. So as a result, basically the leader leveraged the bandwidth of the other validators to propagate the block. And as a result, everyone spends a small amount of bandwidth instead of the leader has to send the block to everyone. So this allows Monad to have a larger block size. So if you compare Monad's block size with Ethereum's block size, you can see that Ethereum block size can contain roughly 200 transactions. Monad has 10K transaction. There is also the Monad block size is large, and Monad's block can be propagated just in 1 second. And then the validators do not have to have higher bandwidth. The bandwidth can be very similar to the, or even lower to what the requirement at the Ethereum is. So how the Raptor cost works? So a leader here can divide the block into coded chunks using erasure coding. So I wouldn't go into details of how erasure code works, but just a high level. And then it sends distinct chunks to each validator, and then validator collects their distinct chunks, and then everyone shares the chunks with each other, the chunks that they have. And then at the end, everyone, once they receive K out of N chunks, then everyone will be able to rebuild the block. And this way, everyone has to send small number of chunks, just small piece of block to everyone else. So no one gets congested because everyone shares a small amount of bandwidth during this propagation. So this kind of allows the bandwidth requirement to be low for the validators in the network and allows the network to have larger block size. And then the next improvement is in the asynchronous execution. So generally blocks and execution and all the traditional consensus protocols are interleaved. So what do I mean? They are kind of connected together. So if we see Ethereum like this, if this is the full block time, which is generally 12 seconds, then a small portion of this 12 seconds, maybe 100 milliseconds or something like this, is allocated for the execution. And then the rest is allocated for the block time, for the block propagation. So if you see, so this time is pretty small, and then the block size is also small. So this causes a contention and competition among transactions to be included in the block and to be executed. So that's why it causes escalation or increase in the fees. And that's how it works. You have a block, and this is the execution time, and then we have the block time. And they are also ordered serially. So one block is executed. Yeah, so plus, previous block propagation time execution, then current, and then the block that is propagated, executed here, and then the next one is propagated. So it's kind of, you see, it's in a serial order, and execution does not get enough time. That's why the fees is so high. So there's a mechanism called asynchronous execution where you don't have to do serial execution. This means you can propagate a block and then you perform execution while you are propagating another block. So now kind of this block time and execution time are kind of pipeline. So you can do this in parallel. This is called asynchronous execution. So basically you are kind of saving a little bit and the block plus execution time. But what we do here is optimize asynchronous execution. So when you do the asynchronous execution, if we see here, you have all this time as already available for execution. This time, because during this time, the other block is propagated. So you can allocate this time to execution. So now execution time is increased. So if you see, so this means that you can have more transactions or more operations within the block because the time for execution has increased. And since the block size is already large, you can include more transactions. So this basically reduces the fees and reduces the competition for the block space and execution time. Yeah, and this, since the consensus and execution are kind of running in parallel, so it also improves the latency for the transactions. So it makes it faster and more efficient. The other improvement that has been done in the Monad is the parallel execution. So if you so we all know how parallelism works. So you execute to do specific operations multiple operations at the same time. So generally, the traditional protocols or execution environments, they order, so transactions are ordered serially and linearly, and then they are executed in the same way. But if your validator has multiple cores, then why not leverage them? Why not use them? Why do we have to execute everything serially? So that's where we another improvement of Monad comes. It's called optimistic execution because when we are executing transactions in a parallel manner or parallelly, there might be cases when transactions touch the same slot of the memory or same variable, or there are dependencies. So those transactions has to run serially. But the transactions that are independent of each other, we can run or execute those in a parallel manner. So initially, the protocol optimistically execute all the transactions at the same time, and then generates results, commit those results. So once results are generated, then the order of transactions are already known from consensus, because consensus gives us some order. And then once the transactions are executed in parallel, then their results are added in such a way that that's equivalent to those transactions being executed in serially. So it's same as those transactions are executed in a serial manner, but it's basically done parallelly. And then there might be cases that some transactions whose input have mutated, or they have dependencies, then those transactions can be re-executed. But this re-execution is cheap because all of the data is already cached in the memory, so you don't have to reload additional data. So it's way cheaper. So as an example, if we see there's a before the execution starts, so there are some accounts that are sending transactions, and whose transactions are included in a block. So one transaction is me. I'm sending 100 USDC to allies. There are some unrelated transactions, and I'm also sending to Bob. And then there's another unrelated transaction. So unrelated transactions plus one of these transactions have to be executed in a serial and in a parallel manner. So this is if we run this in a serial way, in a serial manner, we should get something like this. 100 USDC is deducted from my account. There is some other transaction, and then another 100 USDC is deducted from my account. And each of these 100 USDCs are added to Elias and Bob's account. So this is like the serial execution. And my parallel execution should also be the same, should also give us the same result. So how the optimistic parallel execution works? So basically, it executes everything in parallel. So we don't have to worry about the unrelated transaction because they are already executed in parallel. And for these two transactions that are mutating, we can see the case. So if these two transactions are executed in parallel, so in both cases, my balance is 1,000. And then after deduction, my balance is 900 in both cases, whereas 200 has to be deducted from my account. So what happens in the optimistic execution, that the execution noticed that, there are transactions that are mutated, and one of these transactions goes through, and then, and then the other one fails. And then this one has to be rerun. So when this one reruns, it will use this committed state as a input. And when it uses a committed state, this state has an input here, then it will deduct 100 from this state, which is 900 UCC, and adds it to the ball. So now this is very similar to the serial execution. So the output here we get now is equaling to the serial execution. But again, this re-execution is not that expensive because data is already loaded in the memory and the caches, so it's faster, and hopefully, like that's very unlikely unless all the transactions have such a dependency. Then, and generally, this performance have to be very, very fast. Okay, there are some questions I'm seeing, but maybe I answered it after.
Yeah, Mohammed, thank you. We've been having some sound issues here. So maybe we'll start with any questions in the chat. I think because I think people online have had maybe more of a fuller presentation. So I think you can see, so Mira is asking on integration, what tools or frameworks does Monad offer developers for integrating with other systems or existing projects and products? So if we want to build on Monad, how are we going to do that? Are there tools? Are there?
It's very similar. Yeah, so it's very similar to the EVM or what. So whatever tools that you can use over the on Ethereum, you can use that here. So you can basically take any smart contract that you have in Ethereum and just run it here. It will be just way faster and way cheaper.
Oh, that's great.
And then I will also give the contact details of our developer relations who are like really good on helping anyone who wants to build a project. So they kind of also provide support to build the projects on Monad and any other technical questions that they may have. But generally, it's very similar if you are doing developing or building anything on Ethereum. It's just way faster and way cheaper.
Right. Great. That makes it so much easier for people to onboard. Okay. So I mean, I guess Mir, does that answer your question? There's another one here. Well, let's go to Saw. How do you ensure fund sufficiency if parallel orders exceed available amount? Is this for parallel transactions? Maybe you could speak to that question.
So, as you see that if one execution kind of use all the available funds or one transaction, then the other will fail, and that's fine. The block won't be rejected, but that transaction will fail. Because if you are running transactions in parallel and then multiple transactions in parallel or using the same account, withdrawn from the same account, then as long as then those transactions will be run in a parallel in a serial manner because they all touch the same account, and then then it becomes very similar to the way those transactions are run serially. And once the account balance is less than the amount that transaction withdraws, then that those transactions will all fail.
Great. Does that answer the question, Saw? Oh,
how do you pass through the total amount in the account when you're processing all the transactions?
Okay, let's see. You probably didn't hear that, Mohammed. So what Saul is asking is, how do you pass through the total amount when you're executing the transactions, right? That's what he's really asking about. Not so much the finality, but just passing it through. Maybe you can.
So what does it mean? Does it mean by pass? So initially, yeah, there is some balance. So like whenever a transaction touches,
sorry, I'll just clarify here. What I mean is, considering there are let's say 5 trades placed. Is there a total tally of the amount which is validated against the current account balance? Is there a process that there's a control feature there, or how do you do that?
so the current account track is kept in the state and the MP try that maintains the state, the balance, the current balance of each of the accounts, and then from there, like so initially, yeah, you get the current balance from there, and then you use it.
Okay, thank you.
You're welcome.
Okay. All right. Great. And I think we had another question in the chat from Mir. Is this async execution kind of input output versus CPU burst utilization? The execution is still in a singular bus, and the protocol support the multiple CPU GPU burst to work as used to happen in multi-threaded environment. So I don't know if you can speak to that. It's in the chat if you want to look at the details of the question, Mohammed, but maybe you could answer that.
So
it's quite a technical
didn't
question.
get
You maybe could.
Let me see where I can get the chat and probably leave the. I guess I need to leave the.
Oh, okay. You can't see the chat?
Yes.
Okay. Yeah. So if you end your presentation, maybe you can you'll be able to see the control bar.
Sure.
And see the chat.
Yeah, I guess, okay, I managed to see. And this async execution and the ISP bus utilization, the execution set in a singular bus with protocol support and
it's quite a specific question.
What is the question? What is the question?
So if you want to think about that.
Do you mind if I ask a question?
It seems kind of more statement, or is it a?
Yes, yeah. Maybe could we take it up away from the technical details, and talk about the broader vision for our Modad. So, if people are interested in building on this protocol, which is obviously, has interesting efficiency gains, as you've just described in this presentation, which, speed up transactions, good, enhanced throughput. What are the use cases for this particular protocol that the Monad team is looking to really promote and encourage? And are there funding, grant opportunities available to people to work with Monad to build out particular projects or use cases that they might want to use this protocol for? Can you, maybe this is it's a more of a business oriented question, and it's
it's included in the upcoming slides. Yeah, so there are a few more slides, so we are getting to this. Yeah, so the last improvement is basically the database state access, because if you are improving the execution and the consensus, you also want to access the data fast. Yeah, so just due to time constraint, I will just go to the main the main improvement that here it has done. So and Ethereum, we keep all the account balances and all the information about accounts and smart contracts and a structure called Merkle-Patricia tree. But then this Merkle-Patricia tree and the storage is stored using LSM tree. So basically, if you want to access a node of a Merkle-Patricia tree, so you have to look up multiple nodes. And then when you find that MPT node, then you have to look at through LSM tree to find. So there's like, the cost is pretty high. So what Monad does is that it just have a one Merkle-Patricia tree that is used. So I just have one Merkle-Patricia tree, so you don't have to go through multiple trees to find something. It's just a single one. So this plus parallel reads allow it to have the database access way more faster, and then that kind of improves this throughput to 6,700 operations. And then the use cases that you mentioned. So the current use cases, yeah, it's all these games, CryptoKitties, NFT, airdrops, meme coin, and then future the payments, DeepIn, and all applications that are related to DeepIn, where the location of entity is also important, and then it has to be proven in some way. DeFi, AI, and any other, it's like sky's the limit. You just have to come. But the important part is that now the scaling, so you achieve the decentralization, and also you have this scaling that you did not have before. So, and then you don't have to think about or worry about the high costs of these operations and transactions that you have so this kind of allows you to think about all other use cases that we didn't know or was not possible in future. One of the strengths of the Monad is its ecosystem. And till now, 400 plus projects are supporting Monad, and they are building on Monad. There's a large number of ex-followers as well. And then, yeah, so Monad provides support to developers who want to build on Monad. You can get into the developer Discord and communicate with the other community members, and more. There are also developer relations staff that are there to help you. And then there are, yeah, like Monad Madness pitch competition was there. And then there are also other upcoming future events that will be coming. So there is always chance to communicate, be active in the Discord or other or Telegram, and discuss the projects that you want to implement or Monad, and get whatever help and support that you needed. So it's also possible to get funding, like different like Monad Madness pitch competition was there. But then for funding, generally the bar is really high. So because the resource is limited, So one has to make sure that they have done all the homework correctly to get chances. But the best place is that to get in touch with the developer relation team members, be active with the Discord, and then ask any questions. And so they are really good at providing support and one-to-one support and help. It's technical, or maybe they will also direct you to different resources.
I'm hearing a lot of buzz about Monad, so this is really great, and I would encourage anybody who's interested to join that developer Discord at the link. So there's another question that's just been posted on the chat. So in Ethereum, every state read operation requires a hash to find the slot's location in the MPT. It's beside hashes that we require for dynamic arrays in maps. Is it the same in Monad's EVM version?
Yes, it's the same. Yeah, everything is the same. Like, there are some differences in the consensus mechanism, but it's just. But if you are a developer, you won't feel any difference. Like it's, it's the same. It's just more efficient and cheaper. Yeah.
Yeah, I wanted to ask a question, moving away from like the use cases and sticking on the technical theme. I wanted to ask about, what about security? Since the speed has been increased, and there's always the trilemma. So what sacrifices do we make with security, with the setup, or how can you speak to how security properties have been maintained and are being maintained by the decentralization?
Currently, initially, the goal is that to support hundreds of validators, and then we will be increasing it to thousands of validators. So this kind of makes it less decentralized initially than the Ethereum, but by be able to add more validators, Monad will be in a very specific, unique spot where it has high performance plus high decentralization. And then there is always trade-off. So our goal is that to minimize it, the trade-off, and then we have a specific designs on how we can minimize those trade-offs. But so that's the only difference. And then all other security aspects is basically way more, the guarantees are way more stronger, because there are specific type of attacks that can be done on Ethereum, because the block is not finalized. So there is always possibility that someone can, or some validators can collude to switch the main fork or the fork, or until the fork gets very specific, fork gets very longer or heavy, so that it gets finalized. Where this is not possible, such activity is not possible in Monad. After 2 rounds, you get finalization, and that's done. And to ability to move the forks or fork some blocks and throw them away is provides opportunity for performing a lot of economical attacks. Like you can see someone's block, and then you get and you are the next leader. You see that there's some form of opportunity to do MEV or maximum extraction value, where you can order the transaction in such a way that you get the most out of it. So all of these attacks are pretty easily possible on Ethereum chain, whereas it's way more difficult to be done on Monad. Yes, the main difference is that like we have all the advantage, and then we are in a way to achieve high decentralization. We can still support more validators, but we want to go beyond that. And we have like the mechanism on how to do it. It's just you don't want to have many improvements, deploy many improvements at the same time. That because since all these parts are interdependent, if you deploy all the improvements at the same time, then the chances are that something might break. But if you introduce the improvements a bit slowly, then it doesn't cause interruption in the chain and the protocol.
Okay. I guess the other question I would have for you, Mohammed, is where are you seeing the outstanding technical challenges that Monad is facing right now? So you've done quite a lot of work to deliver this super fast. It's achieving, much greater transaction rates than the benchmark protocols. But what is there left to do yet? What might the research blockchain at UBC work on, for example?
Research for so there are things that led to doing. I guess it's something that all the other chains try to achieve. Like for example, one is that that to improve the censorship resistance. Although currently all the Monad is censorship resistant, the same level that Ethereum is, but still that one leader that proposes the transaction, it has some power to not include some specific transaction or change the order the way benefits it the most instead of the user of the transaction. And there are different mechanisms to do that, but we need to find out the best way so that it can it does not kind of create a huge trade-off between the performance and decentralization that we have. That's like something that we need to do. And then one and in terms of the community, that's like how you encourage the Web2 users to come and join the Web3 and build applications on top of Web3 or come up with new use cases. Although so now Monad has the properties, the efficiency of Web2, but now how you can pitch these improvements to Web2 users or developers so that they can also join and kind of try to take this Web3 to the mainstream, which is our goal overall.
So a technical challenge, a business challenge, and maybe a policy challenge there, mainstream adoption.
I think the regulations are also like something very important. So let's see. Things are kind of changing. So regulation. There are some hopes, but let's see.
What are you sensing? I mean, you're based in New York now. There's recently been an election, and the price of Bitcoin is going up. So generally, there's an optimism in the, let's call it the cryptocurrency sphere anyway, if not Web3 generally. What are you sensing in Monad Lab? Is this are you seeing a kind of expansion?
It's very similar. Like throughout the community, there's like a optimism, but then it depends like how eventually in practice things end up. Like how so
So it's
do we
still
see
kind of
exact? There are
open.
any policies that will help. That's something to be seen, but generally, yeah, there's a lot of optimism. And to to have better policies, and that will kind of allow this technology to go mainstream as well.
Yeah, I guess we'll have to just wait and watch and see, huh? It'll be interesting times.
Yes,
See
yes, yes.
what happens. So moving away from the specifics, just kind of, unless I want to just make sure that I'm not missing anybody. Any last questions from any of our audience here? Yeah, not seeing any questions. So just one last question before we let you go then, because we're at the top of the hour. But what is really exciting you in terms of what you're seeing happening in the blockchain space right now, or Web3 in general? What do you think is the big, the kind of the big trends or exciting things that you're noticing that you'd like to share with the listeners?
So I think there are several good projects who are pushing the boundaries. And then more importantly, there are projects that come with the new use cases that are real use cases, like not just exchanging meme coins or memes. So that's something good. So people are now thinking to come up to use blockchain to address the actual real life problem. And I think blockchain at UBC is doing really good in that aspect. That during my period that I was there, I saw some really good use cases. But I think implementing these projects is not easy. It's quite complex, and it requires a lot of support. And one good thing about Monad is that developer relations. So there are many people whose job is that to help the projects to be able to build a really good product. This kind of encourages me and gives me optimism that eventually we will be able to go mainstream and attract more users and basically make it more common make the blockchain more understandable and usable for common people rather than few elites who knows about technology and its benefits. So I think that's and then since Monad was like initially kind of the pioneer of providing this good support and build a community. So the good thing is that other projects are also now following that. They saw that it's kind of working for Monad. And this, because most of the project initially were like all these technical guys and everyone knows all those in-depth technical stuff. But then in some way we were not really good to transfer or translate this good technological achievements or deliver it to the normal population or to the normal people. And now majority of projects have learned that from this and they are kind of trying to provide the support, engage the community, and try to come with the use cases that are basically usable. That has to be the goal, because we don't want this technology to be used only by some specific people or it remain within that bubble. It has to expand, and it has to be so that the whole humanity can leverage this technology.
Mm-hmm. Yeah, and I'm going to sneak in one last question that is from Amir Hossein. Does Monad want to consider ZK as a scalability tool in its infrastructure. So of course, ZK is like very hot topic right now. And
yeah,
so
yeah, the ZK is very hot topic, but its performance is its performance is not what we can for now use it. It still needs a lot of improvement, but we have it like that in mind. So we have cryptographers who are working on making sure that whenever we are able to integrate ZK with Monad, it should not compromise the performance that we give. Because yeah, with ZK you can kind of maybe minimize some proof sizes but if the computational cost is high, then you don't get that much out of it. So we are like considering it, but for now I think we think that there's some time for this ZK technologies to get some maturity in terms of performance so that it can be integrated.
Good. Yeah, great. Well, listen, we've got to end our session now because we're at the top of the hour. In fact, we've gone a little bit over, but thanks so much. It was really great to see you, to hear about the exciting developments that you're working on.
Thank you, everyone.
Yeah, and we really hope that we can see you in person the next time you come up here. Keep us posted. And yeah, we'll look forward to talking to you anytime. So thanks a lot, Mohammed, for your presentation today. And thank you everybody for joining the Blockchain at UBC Monthly Research Talk. And we'll stay tuned for the next one. So bye for now, everyone. Thank you.